Hello viewers, I am BSSP Rajashekhar, Assistant Professor of Mathematics, Government Degree College for Women, Nalgonda. In today's video, let us discuss about the dimension of a vector space. So this is the class map. Let us first quickly recap the definition of linearly dependent and independent sets and the basis, which are prerequisites for this concept. Later, we will prove one of the statement that if a vector space V has a basis V with some n vectors, then any set in V containing more than n vectors must be linearly dependent. And if a vector space V has a basis of n vectors, then every basis of V must consist of exactly n vectors. We prove these two statements. Later, we define dimension of vector space and we look into some of the examples of dimension. And finally, let us do some of the problems. Let us solve some of the problems on dimension. So let us quickly go through the definitions of linearly independent set and dependent set. An indexed set of vectors v1, v2 and so on vn in V is said to be linearly independent if the vector equation c1 v1 plus c2 v2 plus so on plus cp vp is equal to O, the zero vector in V, has only the trivial solution, zero solution. That is c1 is equal to 0 and c2 is equal to 0 and so on, cp is equal to 0. So if the relation c1 v1 plus c2 v2 and so on, cp vp has only the zero solution and no other solution, then we can say that the vectors used in this relation v1, v2 and so on vp are linearly independent. And if we can able to find a non-zero solution for the same, then we can say that the set is linearly dependent. That is, the set v1, v2 and so on vp is said to be linearly dependent if c1 v1 plus c2 v2 and so on plus cp vp is equal to O has a non-trivial solution. That is, if there are some weights or scalars c1, c2 and so on cp not all zero such that c1 v1 plus c2 v2 plus so on cp vp is equal to O. So if we are able to find some non-zero scalars satisfying this equation c1 v1 plus c2 v2 plus so on cp vp is equal to O, then we can say that the set is linearly dependent. And otherwise, that is, we can't find any such non-zero set, then we can say that the set is linearly independent. Sorry. Whenever the set is linearly independent, there must be only zero solution, except that there will not be any solution for the equation c1 v1 plus c2 v2 and so on cp ep is equal to O, the zero vector. And the definition of basis is that let H be a subspace of a vector space V, then an indexed set of vectors B is equal to B1, B2 and so on Bp in V is a basis for H if the two conditions. First one is B is linearly independent set and B spans H. That is, H is equal to span of B. So subspace spanned by B coincides with H. If these two conditions are satisfied, we can say that B is a basis for H. If we can find a linearly independent set which can span the entire vector space V, then we can say that that set is the basis for the vector space V. So these are the points which we have seen in the earlier classes. With this quick recap of these definitions, Let us move on to today's class. So this is the first statement which we are going to prove now. If a vector space V has a basis B is equal to set of B1, B2 and so on Bn, then any set in V containing more than n vectors must be linearly dependent. So now a vector space and a basis with n vectors are given. We are going to prove that any vectors, any set of vectors in V which has more than this n vectors is linearly dependent. It is given that V is a vector space and B is equal to set of B1, B2 and so on Bn is a basis of vector space V. Let U1, U2 and so on UP be a set in V with more than n vectors. That is, this P is greater than n. P is greater than n. This should be greater than n, not greater than equal to. P is greater than n. For the convenience, let us denote the coordinate mapping x to xb with t. So let now our t denote the coordinate mapping x to xb. So t is the coordinate mapping. Then t is a mapping from v to Rn, and it is a linear transformation. We have already seen that it is an isomorphism. It is a linear transformation and 1, 1 and R2. So here let us take the property of linear transformation. It is a linear transformation such that T of u is equal to ub from the definition of coordinate mapping. Ub is nothing but the b coordinate vector of u. So let A is equal to, let us form a matrix A that is equal to T of u1, T of u2, T of ub. So these are all column matrices. Tu1 is nothing but u1b. u1b is a column vector, column matrix in Rn. So these are the coordinate vector of u1. So that is a column matrix with the coordinates, scalars as coordinates. So using the columns tu1, tu2 and so on tup, let us form a matrix A. Now each tu1, tu1 and tu2 and tup, these are all column matrices with n rows. So it is n by 1 matrices. These are all n by 1 matrices, n rows and 1 column. Since our basis has n vectors, then A has p columns and n rows. Since there are p vectors, tu1, tu2 and so on tup, there will be p columns. And since the basis contains n vectors, each column matrix has n rows. So the matrix A has p columns and n rows, and p is greater than n. Therefore A has at most n pivot positions and hence n pivot columns. It has lesser number of rows, that is n. So each row, each non-zero row contains a pivot, of course. So there cannot be more than n pivot positions in matrix A, since there are only n rows. Since one row cannot have two pivot positions, so maximum there are n rows are there. So maximum we can get n pivot positions. So the columns which has pivot positions are called pivot columns. So there cannot be more than n pivot columns. So you can conclude that A has at most n pivot positions and hence at most n pivot columns. So since P is greater than n, there must be some non-pivot columns. But these non-pivot columns of A are linear combination of preceding columns. So we know that every non-pivot column of a matrix is a linear combination of preceding columns. We have proved that in the earlier classes. So there are some non-pivot columns in A, and these are the linear combination of preceding vectors. So from this we can conclude that the set TU1, TU2, TUP and so on TUP is linearly dependent, since the vectors which are non-pivot columns in A are linear combination of preceding vectors, then the set is linearly dependent. So whenever the set is linearly dependent, we can find a set of scalars C1, C2 and so on Cp, not all 0, such that C1 Tu1 plus C2 Tu2 and so on Cp Tup is equal to O. O is the null matrix 0, 0, zeros, the null zero vector of Rn. So at least one of the C1, C2 and so on Cp is not 0, since it is a linearly dependent set. If all are zeros, then it is linearly independent. But we have got that this set is linearly dependent. That's why there will be at least one non-zero in these scalars. So since T is a linear transformation, this relation C1 T of U1 plus C2 T of U2 and so on Cp T of Up can be written as T of C1 U1 plus C2 U2 and so on Cp Up is equal to O. O is the zero matrix in Rn. So since T is a linear transformation in which we have two properties, T of U plus V is equal to T of U plus T of V, and T of Cu is equal to C times T of U. So this is the combined property of those two properties. Using those two properties, we can conclude this. So let this vector C1 U1 plus C2 U2 and so on Cp Up is denoted by some vector x. This is some vector that is denoted by x. So let x is equal to this vector. We know that from the coordinate systems x is equal to PBXB. That is equal to PB. Here XB is denoted by T of x. P of x is nothing but xp, the coordinate map of x. Here PB is equal to, PB is a matrix formed by using the vectors in the basis of the vector space. So here B1, B2 and so on Bn, these columns will form the matrix of PB. Then x is equal to C1 U1 plus C2 U2 and so on C3 UP. Actually this vector is denoted by x, that is equal to, this is PB and this is XP. That is equal to, after multiplying these two, we will get 0 into B1, 0 into B2 and so on 0 Bn. That is equal to, since all the vectors in this relation are 0 vectors, so we will get a 0 vector of vector space B. 0 vector of vector space is O. That is denoted by O. So since C1, C2 and so on Cp are not all 0, such that this relation holds. C1 U1 plus C2 U2 plus so on Cp UP is equal to O. So these non-zero scalars, some of them are non-zeros. It is a non-zero set, of course. This set of scalars is satisfying this relation. So we can say that from this U1, U2 and so on UP is linearly dependent. From the definition of linearly dependent sets. So this theorem implies that if a vector space V has a basis D with the elements B1, B2 and so on Bn, then each linearly independent set in V has not more than n vectors. Since any set having more vectors than the vectors in a basis is linearly dependent, we can conclude that every independent set must be less than or equal to the number of vectors in the basis. So the number of vectors in an independent set is less than or equal to the number of vectors in a basis. So number of elements in an linearly independent set cannot exceed the number of vectors in any basis. So using this consequence, let us prove one more statement. This shows that if a vector space V has a basis of n vectors, then every basis of V must consist exactly n vectors. So using the previous concept, let us prove that every basis of a vector space has exactly same number of vectors. Let us take two bases for a vector space V. Of course, there will be any number of bases. Let B1 be a basis of V with n vectors and B2 be another basis of V with m vectors. But assume that these two bases have different number of vectors. Now B1 is a basis and B2 is a linearly independent set. So since every basis has two properties, one is linearly independent set, second one is it can span the vector space or subspace which we are taking. So here B2 is taken as a linearly independent set, and now B1 is a basis and B2 is a linearly independent set. So the number of elements, number of vectors in in a linearly independent set cannot exceed the number of vectors in a basis. So M cannot exceed n, that is m less than or equal to n. That is our equation. Similarly, now B2 is a basis and B1 is a linearly independent set. In fact, both are linearly independent sets, both are bases. But here I am taking the property of linearly independent set of B1. So now B2 is a basis and B1 is a linearly independent set. That implies n less than or equal to m. Since a linearly independent set does not contain more vectors than a basis. So with the same argument, here we can show that B1 in which there are n vectors. So this n cannot exceed the number of vectors in the basis B2, that is n. So n less than or equal to n. So from these two equations, 1 and 2, we have n is equal to n. So here B1 and B2 are randomly chosen bases. So we can conclude that every basis of V must consist exactly same number of vectors. So if you find a basis for a vector space, then all other bases must also contain the same number of vectors. For example, in the color printer example, there are 3 base colors. So if you want to find any other basis, then 3 different colors will be sufficient. Of course, they are to be linearly independent. So the problem is to find linearly independent set with that number, with the same number 3. In that case, you have to find 3 linearly independent colors that will form a basis. So any linearly independent set with the same number of vectors will form a basis. So now we can define the dimension of a vector space. So we have seen that in any vector space, all the bases contain same number of vectors. So that number, that unique number, will be called as dimension of a vector space. So if a basis for a vector space B is finite, so here there will be 2 cases. If a basis contains infinite elements, that's a different case. Whenever it is finite, the number must be equal. So if a basis for a vector space V is a finite set, then V is said to be finite dimensional. And the number of vectors in a basis for V is the dimension of V. So that unique number is called dimension, which is common in all the bases. is called the dimension, and it is denoted by dimension of V. First three letters of dimension is taken in the symbol. We call it as dimension. The dimension of zero vector space of singleton set 0 is 0. So there will be no other vector in this zero vector space. We take the dimension of a null space or zero vector space O as 0. If V is not spanned by a finite set, then V is said to be infinite dimensional. That is, there is no basis, no finite basis, no basis with finite number of vectors can span the set. Whenever we are saying that it is a basis, there are two properties. One, it is linearly independent, and second one is it can span this entire vector space V. So, if the basis contains infinite number of vectors, then we can say that V is infinite dimensional vector space. Whenever the basis contains finite number of vectors, we say that vector space V is finite dimensional, and that number of vectors in the basis is called the dimension of vector space V. It is denoted by dimension of V. So this is the definition of dimension of a vector space. Let us look into some of the simple examples. The standard basis for Rn contains n vectors. Those are E1, E2, and so on here. E1 is 1, 0, 0, 0. E2 is 0, 1, and zeros. En is 0, 0, and so on 1. So there will be n vectors, n column vectors for Rn in the standard basis. So dimension of Rn is n. Similarly, dimension of R2 is 2. Since its standard basis is matrix 1, 0 and 0, 1. These two are the vectors in the basis, standard basis of R2. Of course, you can form a different basis with two vectors, with any other two vectors, which are linearly independent. So in any basis of R2, there will be only two vectors. So dimension of R2 is 2. Similarly, dimension of R3 is 3. Here the vectors in the standard basis are E1, E2, E3. Where E1 is 1, 0, 0, E2 is 0, 1, 0, E3 is 0, 0, 1. So you can form the basis for R3 using 3 linearly independent vectors. If P2 is a space of all polynomials of degree at most 2, then the standard basis of this vector space is 1 t square. Since a typical element in P2 is in the form of a0 plus a1t plus a2t square. So the basis for this one is 1 t square. Using these three vectors, you can form any vector, any typical vector in P2. So there are three vectors in the basis of vector space P2. So we can say that dimension of P2 is 3. In general, dimension of Pn, where Pn is a space of all polynomials of degree at most n, is n plus 1. Dimension of Pn is n plus 1. So if you want dimension of P5, that is 6, where P5 is the space of all polynomials of degree at most 5. So since there will be constant terms also, you have to add 1. This one is because of this constant. The space P of all polynomials is infinite dimension. So all polynomials, in the space of all polynomials, you can take any n. N is not finite here. So you can't find a basis with finite vectors, finite number of vectors. So its basis will be 1 t, t square, t cube, and so on. That will be the standard basis for P. It is not finite. So P is infinite dimension. Let us look into one more example. Let H is equal to span of V1, V2, where V1 is a column matrix 3, 6, 2, and V2 is equal to -1, 0, 1. So H is a subspace spanned by these two vectors. Then V1 and V2 is a basis, since these two are linearly independent. How can we say that these two are linearly independent? Here, V1 is not a multiple of V2 and V2 is not a multiple of V1. Whenever two vectors are given, we can easily say that either they are linearly dependent or linearly independent by watching whether they are multiples of each other. Here, V1 is not a multiple of V2 and vice versa. So we can say that these two are linearly independent. So linearly independent and these two can span H. Both the properties are fulfilled. So the set of V1, V2 is a basis for H. So there are only two vectors in the basis of H. So dimension of H is equal to 2. So geometrically, it is a plane. H is a plane containing these two vectors, these two lines, straight lines. This is V1. This is 2 times V1, 3 times. This is a straight line. This point represents V1. Then this line contains linear combination of V1 or scalar multiples of V1. And this line contains scalar multiples of V2. So all the vectors in this plane which is joining this vector and this vector V1 and V2, it's a plane. It represents the set spanned by these two vectors V1 and V2, that is H here. So Each vector has two dimensions, one v1 and second one is v2. So we can say that dimension of H is equal to 2. Find the dimension of the subspace H is equal to set of a matrix, a column matrix A minus 3B plus 6C in the first row, 5A plus 4D as second row entry, B minus 2C minus D third row entry, and 5D in the fourth and last row entry, where A, B, C, D belongs to R. So these are real numbers. A, B, C, D are real numbers, and H is a subspace denoted by this matrix. For different real values of A, B, C, D, you will get different matrices. Those are all form the subspace H. So H can be written as, this H can be written as H is equal to, we can take the common elements out. So A times, here it is 1 time A, in the second row it is 5 times, third and fourth rows A is missing. So A times 1500 plus B times, this is minus 3 times here and absent in the second row, 1 time in the third row, absent in the fourth row. So minus 3, 0, 1 and 0 plus C times 6, 0, minus 2, 0 and plus D times 0, 4, minus 1 and 5, such that A, B, C, D are real numbers. So the given H is written, can be written like this. This can be further simplified as set of AV1 plus BV2 plus CV3 plus BV4, where A, B, C, D are real numbers, where V1 is this first column matrix, this vector, and V2 is this one, V3 and V4. So these four vectors are denoted by V1, V2, V3, V4. Then H is a linear combination of these four vectors. That is, H is span of V1, V2, V3, V4. We can observe that from these vectors, clearly V3 is minus 2V2. Here if you multiply V2 with minus 2 times minus 3 is 6. Minus 2 into 1 is minus 2, remaining are zeros. So from this we can clearly observe that minus 2V2 is equal to V3. Minus 2V2 is equal to V3. And V1 is not a zero vector. Since there are not all zeros, so it is not a zero vector. And V2 is not a linear combination of V1. That is, you can't form this vector using this one. For any multiple, for any scalar of multiple of V1, you can't get this one using this 0. So these two are linearly independent. And similarly, using V1 and V2, you can't get to V4. So for any scalar multiples, the last entry must be 0 only with these two vectors. So here it is 5. So we can say that V4 is not a linear combination of V1 and V2. So V1 is not equal to 0 and V2 is not a linear combination of V1 and V4 is not a linear combination of V1 and V2. Therefore, by skipping or eliminating V3, we can say that V1, V2 and V4 is a spanning set of H and linearly independent. Since V3 is a linear combination of V2, we can omit it. Even if we omit V3, the remaining set still can span H by our spanning set theorem. And we have seen here that V1 is not a zero vector and V2 is not a linear combination of V1 and V4 is not a linear combination of V1 and V2. So these three are linearly independent. So it can span H and linearly independent set. So we can say that this is the basis for H. Set of V1, V2, V4 is a basis of H. So a basis of H contains three vectors. So we can conclude that dimension of H is 3. So here, though there are 4 vectors are used in the given formula, since one is a linear combination of others, that is omitted, and remaining 3 can form the basis for H, and hence the dimension of H is 3. Let us look into some examples of subspaces of R3. Let us classify these subspaces of R3 by the dimension, by using the dimension. The subspaces of R3 can be classified by dimension. First, zero-dimensional subspaces. So, zero subspace, which is a set containing only zero vector, is the zero subspace and its dimension is 0. That will be only 1. And one-dimensional subspace. So, any subspace spanned by a single non-zero vector. So, any multiple of a non-zero vector will be a subspace and its dimension is 1. So, the set of all multiples, scalar multiples of a single non-zero vector is a subspace whose dimension is 1. Such subspaces are lines through origin. So, we can see these two geometrically. So, this origin O, zero vector, itself is a subspace with zero-dimensional subspace, and any non-zero vector can form a one-dimensional subspace with all its scalar multiples. So it is a line. It looks like a line. Any line anywhere. This is a line. You can draw any number of lines. Each line is a one-dimensional subspace, provided that should pass through the origin. And two-dimensional spaces, any subspace spanned by two linearly independent vectors. Such subspaces are planes through the origin. So they will be look like planes. Three-dimensional subspace is only R3 itself. It contains entire space. Any three linearly independent vectors in R3 span all R3. Entire R3. Geometrically, it will look like this. So if you take any two vectors and the plane containing those two vectors is a two-dimensional subspace. Of course, that will pass through the origin. It should pass through the origin. So all the planes passing through the origin will be subspaces of two dimension. So entire space R3 is a three-dimensional subspace. So let us look into some more examples. Decide whether each statement is true or false and give a reason for each answer. Here E is a non-zero finite dimensional vector space. If dimension of V is P and if S is linearly dependent subset of V, S contains more than P vectors. So our theorem states that if dimension of V is equal to P and S is linearly independent, then S must be less than P. But it does not imply that S is linearly dependent. The number of elements in S must be greater than P. So that will not the inference of our statement. So this is false, since we can form lesser number of linearly dependent sets. For example, if we take this zero vector itself is linearly dependent and there is only one vector there. So we can form linearly dependent sets with even lesser number of vectors. We can form more number of vectors than the vectors in the dimension and lesser number of vectors than the number of vectors in the basis or dimension. So the given statement is false. Since we can take zero vector or any combination with zero vector and zero vectors and some non-zero vector, these two form a linearly dependent set. Whenever there is zero vector in a set, that is linearly dependent. So we can form any number of sets with any number. So this is another statement. If S spans V and if T is a subset of V that contains more vectors than S, then T is linearly dependent. The set S spans V and T is a subset that contains more vectors than S, then T is linearly dependent. So this statement is true since by spanning set theorem, every spanning set contains a basis. Every spanning set can be reduced to a basis. So let it be S dash. Then S dash must have lesser elements than S or equal number of elements to S. But since T has more elements than this S dash, so it must be linearly dependent by our previous theorem. Any set containing more vectors than the basis is linearly dependent. So T must be linearly dependent. So the statement is true. With this, I am concluding today's class. Thank you very much.